Hi there, and welcome to this lesson on Pure Mathematics 3. And in this lesson, we'll be looking at how you use iterative formulae in order to find the solution of an equation. To solve any equation of the form f of x equals 0, we rearrange the equation into the form x equals some other function of x. What that means in practice is we've got some function of x on the left-hand side, and we try and keep one x on the left-hand side and move everything else onto the right-hand side. And then once we've done that, we then rewrite this relationship, x equals g of x, as the iterative formula, xn plus 1 is equal to g of xn. For example, given the equation x squared plus 4x minus 1 equals 0, first of all, show that this can be rearranged to give the equation x equals 1 over x plus 4. And then secondly, using the resulting iterative formula, xn plus 1 equals 1 over xn plus 4, find x1 given a starting value of x0 equals 1. What that will mean is we substitute n equals 0 into this formula. And then by finding further iterations, calculate this solution to the quadratic to 3 decimal places. Okay, I'll let you see if you can work your way through this on your own. So pause the video, have a go at making sense of all of this, and then come back to me again when you're ready. Okay, let's have a look. So first of all, show that this equation can be rearranged to give the equation x equals 1 over x plus 4. So we take that quadratic, and what we do is we factorize the first two terms so that you get x into x plus 4 minus 1 equals 0. Then adding 1 to both sides gives us that. Dividing by x plus 4 gives us what we were trying to get, x equals 1 over x plus 4. And then this relationship becomes the iterative formula, xn plus 1 is equal to 1 over xn plus 4. Part 2 asks us to use that resulting formula in order to find x1, given a starting value of x0 equals 1. What we do is we substitute n equals 0 into the formula. And when we do that, what we get is x1, which is what we're trying to find, equals 1 divided by x0, that we know, plus 4. That gives us x1 is equal to 1 over 1 plus 4, which is 1 divided by 5, which gives us x1 is equal to 0.2. Okay, and then part 3 asks us to repeat that process, doing further iterations in order to calculate this solution to the quadratic to 3 decimal places. So we began with x0 equals 1, we then worked out that x1 was equal to 0.2, and we now need to put that value into the iterative formula, which gives us 1 over x1 plus 4, which is 1 over 0.2 plus 4, which gives us 0.238095. We then put that value into the iterative formula, which gives us this, which gives us 0.235955, and we then just keep on doing this. So we then put 0.235955 into the iterative formula, and for the answer, that gives us 0.236074. Now, we've been asked to calculate the solution to 3 decimal places. But if you have a look at what we've been doing so far, we started with 1, then the next solution went down to 0.2, and the next iteration took us up to 0.238. The next iteration took us down to 0.235. The next iteration took us up again to 0.236. So these iterations are oscillating. They're going down, then up, then down, then up. What that means is that the real solution is always between any pair of solutions. So the real solution will be between 1 and 0.2. It'll be between 0.2 and 0.238. And by the time we get down here, we know that the real solution will be between 0.2359 and 0.2360. Now, any number between those two will be 0.236 to 3 decimal places. So at this point, we can stop and say that the solution to the quadratic to 3 decimal places must be x equals 0.236. Now, when a solution is converging, like in the previous example, there are actually 2 ways in which that can happen. We were solving the equation x equals 1 over x plus 4, which was the rearrangement of the quadratic. And when we solve this equation, what we're finding is the intersection of the graphs y equals x and y equals 1 over x plus 4. Well, we can draw that. Y equals x would look something like that, and y equals 1 over x plus 4 would look like that. Now, there are actually 2 intersection points for those, for the curve and the straight line. There's one here, and there's one down here. The one that we found was the solution x equals 0.236, which will be this solution up here on the right-hand side. Now, we need to look at this a little bit more accurately. So we're going to magnify this part of the graph around the solution, and you get something like that. So we started with the value x0 equals 1. You're always given the starting value in these questions. And x0 equals 1 would be here at x equals 1 on the x-axis. What we then did with that value was we put it into this function. So we put it into 1 over x plus 4. And you can show that with the dotted line here on the diagram. When we got the answer to that, we then used that answer as the next value of x. And you can show that by drawing the dotted line over here to the line y equals x. Once we got that new starting value, which was x1 equals 0.2, we put that back into this function again, which you can show with this dotted line. Once we got the answer, we use that answer as the next value of x, which gives us that dotted line. And the next iteration, which was x2 equals 0.238. Now, that process carried on, but it gets very, very hard to see what's going on, even on this diagram. But that type of iterative process leads to what is called a cobweb diagram. And if we were to show a few more steps on a diagram, then you can see why it's called a cobweb diagram. What you get is something like this, where the starting value was here, you put that into the function, that gives you the next value of x. You put that into the function, that gives you the next value of x. You put that into the function, that gives you the next value of x, and so on, as you spiral inwards towards the center and towards the solution. In terms of the values you actually calculate on your calculator, it would be these values. So you're given x0, x1 would be the first value you calculate, then x2, then x3, then x4, then x5, as we oscillate in towards the solution. Now, there is another possibility. You can have an iterative process that doesn't oscillate like that one, where it goes from one side to the other side. Instead, it just approaches the root from one side only. If you have something like this, where the first solution would be down here in the bottom right-hand corner, and that solution you'd be given, and you'd put it into the function. When you put it into the function, you get the next value of x, you put that into the function, you get the next value of x, you put that into the function, and so on, as you converge from the right-hand side towards the real solution. And this is called a staircase diagram, again, for obvious reasons. The values that you'd actually be working out on the calculator would be these values here. So you're given x0, you calculate x1, then x2, then x3, then x4, then x5, as you converge towards this solution here. Now, iterative formulae do not always converge on the solution, like those 2 cases did with the cobweb diagram and a staircase diagram. It is possible that the iterative formula won't work and that it'll diverge away from a solution. If you had something very similar to the last example, but where the 2 lines have been swapped over, and if you started here with x0 very close to the solution, You put that value into the function, and then once you've got the solution from the function, that becomes the next value of x. You put that into the function, that becomes the next value of x. You put that into the function, that becomes the next value of x, and so on. And each time you're moving away from the solution. You're not going towards it, you'd be diverging from the solution. Okay, let's have another look at how these things work out in practice. So example 2. Show that the equation, and it's a cubic equation, x cubed plus 3x squared minus 7 equals 0. Show that it has a root somewhere between x equals 1 and x equals 2. Now to do that, you'll need to use the technique that we learnt in the last lesson, where you look at change of signs. And then part 2 asks us to show that the cubic equation can be rearranged to give the iterative formula xn plus 1 is equal to the square root of 7 minus xn cubed, all divided by 3. And then using that formula and a starting value of x0 equals 1, we're asked to find a solution to the cubic equation accurate to 1 decimal place. Okay, I'll let you have a go at doing this yourself. Pause the video, have a go, and come back to me when you're ready. Okay, let's have a look. So first of all, we've been asked to show that this equation has a root between x equals 1 and x equals 2. So we need to find the value of the function at 1. And if we put 1 into the function, we'll get 1 plus 3 times 1 squared minus 7, which is minus 3. The significant thing about that number being the minus. Then we put 2 into the function. And if we put 2 in, we get 2 cubed plus 3 times 2 squared minus 7, which is 13. The significant thing being that it's plus 13. So because there is a change of sign from minus to plus between f of 1 and f of 2, and because f of x is a continuous function, then there must be a root somewhere between x equals 1 and x equals 2. Part 2 asks us to show that the cubic equation can be rearranged to give the iterative formula xn plus 1 is equal to the square root of 7 minus xn cubed over 3. Well, if we've got the cubic equation and we just move the 7 and the x cubed to the other side, we'd get that. Then dividing through by 3, we'd get that. And then finally square rooting both sides. That gives us the relationship which will become the iterative formula when we make this xn plus 1 and the x cubed xn cubed. So that's the iterative formula we'll be using. And then in part 3, we're asked to use the formula in order to find a solution accurate to 1 decimal place. So the starting value is x0 equals 1. And then by substituting n equals 0 into this formula, we'll get x1 is equal to the square root of 7 minus x0 cubed divided by 3, which is 7 minus 1 cubed divided by 3, which gives us x1 is equal to 1.4142. And then putting that value into the iterative formula, we would get this, which gives us x2 is equal to 1.1792. Putting that value into the iterative formula will give us x3, which is 1.33669. Carrying on, x4 will be that, x5 will be that, x6 will be that. Now, this particular formula, it is converging, but much, much more slowly than the first formula that we looked at. We've only been asked to find the solution accurate to 1 decimal place. Well, let's look at how we're doing. We know the solution's somewhere between 1.3 and 1.2. So to 1 decimal place, it is either going to be 1.3 or 1.2. Now, x7, if we work that out, we get 1.28. We don't really need that value. We could have either compared these two values or these two. If we compare x6 and x7, what we know is that the real solution is somewhere between this pair of values. Now, if it's between 1.26 and 1.28, that means the solution will round to 1.3 to 1 decimal place. We could actually have worked that out one step earlier, because if you look at x5 and x6, the real solution is between 1.3 and 1.26, and again, all the numbers in that range would actually round to 1.3 to 1 decimal place. Anyway, the solution must be 1.3 to 1 decimal place. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 165 and have a go at exercise 8b. Thank you very much for listening, and cheerio.